Hello! In the previous video, we discussed integration and how the position of a body is updated based on the forces applied on it. In this video, we will explain how force leads to angular momentum and how this is modeled in physics simulations. Angular momentum is the rotational counterpart of linear momentum. The center of mass, also known as the center of gravity, is the mass-weighted average position of all mass in a body. It can be located at any point inside or outside the body depending on how mass is distributed. It is the point where the mass is balanced most evenly. When a force is applied on a body outside its center of mass, it generates rotational motion. We call this effect torque. This occurs because the force is acting away from the point where the body's mass distribution is most balanced. Since the body is constrained by its rigidity, the resulting imbalance causes it to rotate around its center of mass. When a force acts directly through the center of mass, it acts through the point where the body's mass distribution balances. Because there is no imbalance, no rotation is generated and the body just accelerates linearly. Angular momentum is conserved. This means a rotating body will continue spinning forever unless it is acted upon by an external torque such as air drag. The exact formulation for mass treats the body as a continuous density field. This requires integrating across the entire mass distribution, which is computationally impractical for real-time physics. Rigid body systems approximate mass distribution using simpler models. To understand these models, we must first understand what a tensor is. Tensors generalize scalars, vectors, and matrices within a single framework. They allow us to store and transform information. We can use them to transform angular momentum into angular velocity. A tensor's rank indicates the amount of information you need to locate a specific element within it. For a single scalar, the rank is 0. For a one-dimensional array, the rank is 1. For a two-dimensional array, the rank is 2. The simplest model that captures rotational resistance is the mass moment of inertia. This represents the distribution of matter around a single axis, which determines how resistant to rotational motion the body is around that axis. It can be stored in a single float, which is a rank 0 tensor. This representation is used in 2D physics engines. The inertia tensor is the three-dimensional equivalent of the mass moment of inertia. It stores how mass is distributed along all three rotational axes relative to a body's center of mass. It is encapsulated inside a 3x3 matrix to capture each Cartesian axis, as well as the coupling between axes which occurs when a body has asymmetric mass distribution. This tensor has a rank of 2, so it needs 2 values to locate each element. Angular velocity is often represented by the Greek letter omega. It points along the axis of rotation, but it is not equivalent to it. Its direction represents the orientation of the rotational axis, while its magnitude represents the rotational speed of the body. The equation for angular momentum can be written as the following. The inner cross product computes the linear velocity of the mass element due to the body's rotation. This velocity vector is perpendicular to the axis of rotation and the position vector. Taking the cross product of the position vector and linear velocity produces a rotational vector for the mass element relative to the origin. Multiplying it by the mass gives the angular momentum. When the body is symmetric, this vector is parallel to the axis of rotation. Otherwise, it is not necessarily so. The integral represents the summation of all the angular momenta of the mass elements throughout the body. The inertia tensor maps angular velocity to angular momentum through this equation. Ixx is the moment of inertia about the x-axis. Iyy is the moment of inertia about the y-axis. Izz is the moment of inertia about the z-axis. Each one represents the sum of all mass elements multiplied by the square of their perpendicular distance from the corresponding axis. The further the mass is from a principal axis, the harder it is to rotate around that axis, because the further it must travel to rotate by an equal angle. The reason why the moments of inertia are proportional to the square of the distance is because the distance leads to two simultaneous amplifications. Firstly, an element that is 6 units away from the axis of rotation compared to another that is 3 units away will move at twice the velocity and thus has twice the momentum when the elements have the same mass. Secondly, distance creates rotational leverage. A force applied further from the axis produces more torque. This is why it's easier to open a door at the handle than near the hinge. These two factors combine, and since both scale with distance, the result scales with distance squared. The elements outside the main diagonal are called the products of inertia. They represent how mass is distributed along mixed axes. When a body has symmetrical mass along its principal axes, these elements cancel out to zero. They do not measure rotational resistance like the moments of inertia. They measure how mass distribution couples motion between axes. For example, if a mass element is at 4 units on the x-axis and 3 units on the y-axis, and it has a mass of 2 kilograms, its product of inertia will be minus 24. If it has the same mass at negative 4 on x and plus 3 on y, it will be plus 24. The two values cancel to zero. If mass is distributed unevenly, rotating around one axis can partially cause rotation around another axis. The products of inertia can contribute to wobbling and gyroscopic precession. The inertia tensor in 3x3 matrix form has redundancy. For instance, the xy and yx elements store the exact same values. This symmetry is necessary if we want stable rotational energy behavior in orthogonal principal axes. Many game engines store only the 6 unique values, then reconstruct the full matrix when necessary. To ground this theory, let's look at some examples. For a solid sphere, we calculate the inertia tensor using a coefficient of 2 over 5, which is 0.4. For a hollow sphere, we use 2 over 3, which is approximately 0.666. Assuming the hollow and solid sphere have the exact same mass, the inertia tensor is higher for the hollow sphere because more of its mass is distributed further away from the center of rotation. The mass elements must travel further and faster, whereas the solid sphere contains much more of its mass closer to the origin, so it travels a shorter distance. For a solid disk lying flat on the xz plane, the inertia coefficients are 1 over 4 for the x and z axes and 1 over 2 for the y-axis. The y-axis coefficient is larger because less of the disk's elements are closer to the axis of rotation than for the x and z axes. You can understand this intuitively by noticing that the z-axis intersects a longer dimension than the y-axis does. Now that we understand the theory, let's look at an implementation. We initialize a solid box with its dimensions and mass as parameters. The inertia coefficient for solid boxes is stored in the Physics Manager class because we only need one copy of it. We use 3 versions of the inertia tensor. 1. The local inertia tensor, which represents the mass distribution relative to the entity's local rotation axes. This isn't used whilst the physics simulation is updating, so you can just create it on the stack, unless you want to use it for debugging purposes later. 2. The inverse local inertia tensor. This exists because otherwise we would need to do an expensive inversion of the local inertia tensor every frame. 3. The world inverse inertia tensor. As the entity rotates, its relative orientation to the world changes. We need this world relative tensor for the simulation. Recall the earlier examples of the disk, which has more rotational resistance about the y-axis than the x or z axes. As the disk rotates, those axes no longer remain aligned with the world's axes, so the simulation must update the tensor to reflect that. We use the invert matrix function to initialize the local inverse inertia tensor. Because the inertia tensor matrix for a solid box is diagonal, it would be faster if we just got the reciprocal of the three elements. But for non-symmetrical shapes, you would need to use the inversion function. If the entity starts with its rotation axes aligned to the world axes, then the global inverse tensor is identical to the local inverse tensor. Otherwise, we perform the two matrix concatenations that you see here. First concatenating the orientation matrix with the local inverse tensor, then concatenating the result with the transpose of the orientation matrix. The transposed orientation matrix on the right rotates the world space angular momentum into local space coordinates, where the local inverse tensor transforms it into angular velocity. The orientation matrix on the left then rotates the resulting angular velocity back into world space coordinates. To apply a force that will generate angular momentum, we use the apply force at point function. It has parameters for the force vector and a point of contact. For the linear force, we merely add it to the force accumulator. For the torque, we create a vector between the contact point and the center of mass. Because the entity is just a solid box, the center of mass is equivalent to its central position. We then accumulate the torque with the cross product of the offset vector and the force vector. We can see in this image how the resultant torque vector is perpendicular to both vectors and creates an axis of rotation for the entity. In the update function, we first attenuate the torque by applying air drag to it. Since air drag is proportional to the speed of the entity, we calculate this by multiplying the current velocity by the magnitude of the speed multiplied by an angular drag coefficient. A smaller coefficient produces slower damping. A larger one converges faster to rest. The appropriate value depends on the mass of your objects and the effect you're trying to achieve. After we have integrated the drag into the torque, we integrate the torque into the angular momentum. You might be wondering why for linear motion we derive acceleration from force and mass and then integrate it into velocity, whilst for rotational motion we integrate torque into angular momentum and then derive angular velocity. For linear motion, mass is assumed to remain constant, so velocity and momentum are directly proportional. For rotational motion, the inertia tensor changes relative to the world as the entity rotates, so we need to keep track of angular momentum and derive angular velocity each frame. This is where the operation for converting world space angular momentum into world space angular velocity takes place. We then integrate angular velocity into the orientation matrix. We grab a 3x3 submatrix of the 4x4 orientation matrix, and then pull out the rotation vectors. We then update these vectors by integrating them with the cross product of angular velocity and themselves. Since cross products produce a zero vector if the input vectors are parallel, any of the basis vectors that are parallel to angular velocity will not change. Floating point accumulation causes the basis vectors to drift from unit length and lose orthogonality over time, so we normalize them every frame before updating the orientation matrix. At the end of the function, we update the global inverse inertia tensor to account for the current orientation, and then reset the torque because it has already been applied. As we look at an example of applied angular velocity with linear velocity turned off, we can see the entity spinning and how the spinning slows down due to air drag. When we turn linear velocity back on, we can see the angular velocity in tandem with it. If you'd like to help me continue producing in-depth videos on game physics and engine development, consider joining my Patreon. Your support helps me spend more time researching and creating this content. Thanks for watching.